Okay. So we just, before the midterm, we just started talking about arrays, right? I don't think we haven't like drawn pictures of them or anything like that. Okay, got it. We don't own everything. All right, and I'm recording. Yes. Okay. So just to kind of review on this slide a little bit, one thing we might want to do in our programming is we might want to create collections of things. Right now, we're able to create like an int a is equal to 5, or a char c is equal to a question mark, stuff like that. We're able to store a single variable name with a single value associated with it. Well, sometimes we want to have a collection of values. Like we might want to have like a list of numbers, something like that, where we have a single variable name and have 20 numbers associated with that. All right, and we do this through something called an array. So there's some important aspects of an array that we need to really consider. And actually, this concept is the foundational piece for the third computer programming class, CSC200, which is the data structures class, because it talks about what happens when we need things not stored in what's called contiguous memory. So we'll kind of see that here today. So we want to hold multiple numbers. Now, the idea here is that arrays live in something called contiguous memory. So what is contiguous memory? Contiguous memory is memory that lives right next to each other in our system's memory. All right. Now, when we think about our system's memory, our memory inside of our computer, let me hide this somewhere. Let's go there with it. We could think of our computer memory kind of looking like that. Just a whole bunch of little buckets. All right. Now, when we talk about memory addresses, which we're going to be starting to talk about quite a bit here now, when you hear the word address in terms of real life, what does an address mean to you? Like if you ask somebody for their address, what are you asking them for? Yeah, where they live. And what do our addresses look like in real life? Okay, so we usually have what, like a street number, a street name, a city, state, country, right? Potentially, right? So we can kind of create an address that takes us, that gets us to any place on the planet. Is that a fair enough statement? But in order for us to accomplish that as human beings, our addressing is fairly complex. We have to have a whole bunch of different pieces that all work together that ultimately tell us where something is. Now, what's interesting is in computers, when we start looking at memory addresses, they seem scary because usually memory addresses are represented as hexadecimal values. Well, why do hexadecimal values seem scary? Well, because they got letters and stuff, and that's not a normal looking number to us. But the reality is that if we envision our computer as being like in real life, everybody on the entire planet lives on one street, one gigantic long street. And we have somebody who lives at house 0, and somebody lives at house 1, and somebody who lives at house 2, house 9, house A, house B, house C, because now we're counting in hex. Make sense? Okay, so these are hexadecimal buckets. So now our computer, let's say that each bucket of memory in a, we'll just kind of put this in context. So most of our modern operating systems are 64-bit operating systems. Okay, so 64 bits is 8 bytes. 8 bytes big, right? 64 divided by 8, a byte is 8 bits. So this is 8 bytes. The size of a single memory address. Now, realistically, depending on your operating system, that may or may not be exactly true. For instance, modern versions of Linux use a 48-bit address because they have a 12-bit or 14-bit, 16-bit address used for super user stuff. But for our argument here, we're just going to say that memory addresses are 64 bits big.
So for a 32-bit
4 bytes. Yep. And that's nothing new. That's just converting between bits and bytes. 64 bits and 8 bytes are the exact same value, said out loud 2 different ways. Right? Just like I could say the number 14 in decimal, then I can convert it to octal and give you the same value in a different language, something like that. All right. So if we have 8 bytes is the size of a single memory address. Now, how much memory is in our average consumer computer today? Maybe 8 gigabytes. Okay, so 8 gigabytes of memory. So 8 gigabytes is how many bytes? 8 gigabytes is how many bytes? So go ahead and take a minute and figure out what 8 gigabytes is in bytes. We're doing the conversion. I think that is going to be extremely low. That might be the number of megabytes.
Oh, yes.
So 8 gigabytes is 8,192 megabytes, which is 8,388,608 kilobytes. Which is that number in bytes. So that's how many bytes are in 8 gigabytes. So now we want to know what's up. Yeah, but I would multiply that 8 if I wanted to go to bits. But right now I want to go, I'm staying at bytes. So this is gigabytes, megabytes, kilobytes, bytes. So this number right here is the number of bytes that are in 8 gigabytes. But now I've said that each of our memory addresses is actually 8 bytes big. So if we have 8 gigabytes of memory, we have, what is that? 1,073,741,824 unique memory addresses in 8 gigabytes. We'll call this unique 64-bit or 8-byte memory addresses in 8 gigabytes. All right, so we're going to envision a world that is 8 gigabytes in size. It's all one big long street. There are 1,073,741,824 houses on that street. That's the number of individual things we can put in memory if you have 8 gigabytes of memory. Assuming each of those plots of land is 8 bytes big. Depending on your operating system, they might treat the plot of land as a different size, but this is good enough consistent numbers for us here. All right, so I have 1 billion plots of land in which I could build houses, so to speak. And each of those houses has an address. As I walk down the street, this is house 0, house 1, house 2, house 3, house 4, so on and so forth, all the way up to house 1,073,741,823. Because it's 0 indexed. Okay. But in this digital world, all of these houses live on one street and they're all right next to each other in memory, right? We don't need to have memory addresses. We don't need to have memory addresses go into the details, the granularity that we have to have as human beings, where we say street number, street name, city, state, all these things that ultimately zero us in. I mean, because we could have a 123 Elm Street. There's probably 123 Elm Streets hundreds of times in the United States is my guess, because there's probably an Elm Street in all sorts of towns all across the country. All right. But the idea is that we don't need that level of detail with computers because our street's one big long street. So reality is addresses in computers is far simpler than addresses in that we deal with as human beings. And none of us sit awake at night stressing about the complexity of street addresses in real life, do we? That's something we kind of figured out when we were kids. You know, we had to learn our own address, learn our own phone number, and then, you know, that kind of stuff. And we kind of had to find our way home. And then we started driving or riding our bikes to places, whatever it was. And, you know, actually now you probably do. We're probably moving in a direction where addresses aren't really meaningful anymore, right? You just put in the names of places and you follow the blue line. and it takes you there. It's like, oh yeah, isn't that off you know, Jones Street? I have no idea. It's where the blue line tells me to go. If it says make a left, I make a left. Okay, that's the
Right now.
you know, it actually is kind of interesting that we are down well down that path now, right? Same thing with phone numbers. You know, like we don't know most of our friends' phone numbers. We tell our phone to call them. Look, I'm thinking with confidence, I only know 2 phone numbers, mine and my wife's. Could probably make a pretty decent guess at my mom's. But I'm thinking I'm going to miss numbers. Is going to be the problem. All right. So in any case, this is the number of unique memory locations if you have a computer with 8 gigabytes of memory. All right. So that means when we create an array, when I say Windows or Mac or Linux, I want to create a single variable, maybe called AR, and I want this guy to be able to hold 10 integers. Okay, this is the syntax for an array. This is asking the OS to find us 10 unoccupied plots of land, in our example here, in a row that it can sell to me for me to store my integers on.
How does it matter what size the integer is?
And int has a size, whatever the operating system says the size is. Yeah, keep things pretty arbitrary at this point. I need plots of land big enough to hold 10 of these dudes,
Gotcha.
however big those dudes are.
Gotcha.
All right. So in most operating systems, most programming languages, an int is 32 bits for bytes. So that means really what I'm asking for here is 40 total bytes of memory. Make sense? I'm asking for 40 total bytes of memory in a row. So the operating system is going to go to work, going to send out a real estate agent and go and find some place in memory where there is 40 bytes, 40 contiguous bytes of memory right next to each other. All right. The OS will discover the location of 40 bytes of memory in this case, right next to each other, and return to me the address of the beginning of that land. A lot of times this is called the base address. All right. So if we think about this from a real life perspective, if you know you're going somewhere that's a 4-acre property, and somebody gives you the GPS location to the very start of the property, and let's just say it's a skinny property, just goes 4 acres that way, okay? So you know that once you get to the beginning of the property, you can walk for 4 acres until you leave that property, right? Because all that land is associated with that single farm or whatever it is, okay? But all we needed to know to get to the property was the beginning of it, the base address of it. And because I know that those 4 acres, keeping it kind of talking about real life, those 4 acres are right next to each other. I don't have to jump to the next community over to get to acre 2, right? All 4 acres are laid out in front of me. I know I can just start walking, and I'm still at the farm. I'm still at the farm. I'm still at the farm. I'm still at the farm, so on and so forth, right? Same thing's true in computers. Because our arrays are stored in contiguous memory, because we asked our operating system in this case to go find us 40 bytes of memory right next to each other, and it's going to come back and say, this is where your land starts. Here's the base address for the beginning of your array. And then you know from that point, you have 40 bytes of runway that you own. It's all yours. Because the operating system, you asked it for 40 bytes, it came back and said, I found you 40 bytes, this is where it begins. Make sense? Go ahead. So now that becomes a thing of the, so he's asking what would happen if our memory was all filled up. Or even if it wasn't completely filled up, it was unfortunately filled where we didn't actually have a place where 40 bytes existed in a row. Maybe we have 40 bytes total free memory, but not next to each other. At that point, it becomes a problem of the operating system. The operating system gets to decide, how are we going to handle requests from user programs that ask for memory that isn't currently available? Most operating systems will do something with like virtual memory and do swapping out of real memory to the hard drive to kind of make it work, but that's where your computer is going to start feeling very slow. It's having to do that kind of stuff pretty often. And it's not just for this kind of example, but any sort of example where it's needing something that it wants to be in real memory, but it is actually stored in virtual memory, which is typically on the hard drive, which is a lot slower than real memory. That time it takes to swap it with something that's in real memory takes time. And presumably when you're swapping it, you're taking something out of real memory that, what if you need that in 2 seconds? Now you got to find a way to bring that guy back in. Becomes a problem. You'd be better off having more memory if you're often running into a situation with the way you're using your computer. You're asking the OS, you're asking your computer for access to more memory than you physically have. You want to pretty much avoid using virtual memory as often as you can. Okay, but I would say most modern OSs would find a way to make it happen at the cost of performance. Well, it'd still do the same thing. I mean, it would still, if you had 16 gigabytes of unified memory that's on the chip, fine, that memory is faster. In fact, that maybe even makes it worse, because if you're having to swap with a hard drive, the speed difference between your unified memory that's right on the processor and your hard drive, your solid state drive, is probably more drastic than normal memory compared to the solid state drive. Well, the speed between your processor and your unified memory on the CPU is 400 gigabytes per second. Super fast.
Even the SSD.
Yeah, that's faster too, but it's not 400 gigabytes per second. So you still have a slowdown. I would guess that that speed is a greater difference would be my guess. But anyway you cut it, you want to have more, you want to have enough system memory to do the stuff that you're going to use your computer for. You don't want the operating system to have to fake it for you. If it's faking it for you too often, your computer's going to feel sluggish. Or you could have 128 gigs of RAM like him and just run his whole OS and just everything in RAM. Just everything is stored. I don't even use a hard drive. Just it's in RAM. If you actually use all that RAM, what are you doing? Okay. So you're doing rendering stuff? Okay. Mining Bitcoin is not going to necessarily benefit from a lot of RAM. It's going to benefit from GPU compute. But the word he used, the RAM disk thing, that's saying I'm going to take a chunk of my system memory, which presumably is way faster than a solid state drive and way, way, way faster than a traditional hard drive. And I'm going to treat that as a hard drive. So now it's a super fast hard drive. But he's only using 32 gigs of it. That's child's play. Yes. All right. Well, that's true. But then it just reloads in from the disk. But while his computer's on, he has a very fast drive. Okay. Okay. So the idea here is that presuming we have enough memory to do all your jobs, which is what we should probably focus on in our situation here. When we go to ask the computer saying, hey, I want to create a single variable named AR, and I want to hold 10 of these guys in there. You're asking the operating system to go find you, in this case, a plot of land big enough to hold 10 integers, where an integer is 4 bytes big. I'm just telling you that's what an integer is in most languages. So you're asking the operating system, go find me 40 bytes next to each other. All right. And then what that's going to bring you back I'll fix it on the flip side. So we're going to have our variable AR, and AR is going to hold a value. I just made up the value that got returned. Okay, so the operating system came back and said, hey, I found you 40 bytes of memory at memory location 100. Okay, but right off the bat, when you see this, this should feel a little intimidating, right? Because it's a hexadecimal number and it's like, oh, I don't like that. At least it doesn't have A's, B's, and C's and stuff like that in there yet. Okay, but it's bad enough as is. But if we want, for our example, we can operate off this in decimal for us, because we know that 100 in decimal has its equivalent in hexadecimal, right? There's a hexadecimal equivalent to that value, and we're talking about the same thing. We're just expressing it differently. All right, so we'll say it's the address we got back is bucket 100 decimal in our memory. Okay. And we're going to say that AR in this case is something that's called a pointer. Where's my, oh, it's up here. So Add a slide here. Pointers terrify people. Pointer. This is a primitive type variable that is built to hold a memory address. Just like an int holds an integer, a char holds a char, which is an integer, so on and so forth. Okay, we already have all these types that are less scary to us, right? We have a variable type called an int that knows how to hold an integer. We have another variable type called a char that knows how to hold a char. We have another type called a Boolean that knows how to hold a Boolean. We have a double that knows how to hold a double, so on and so forth. Now we have a new type called a pointer. And pointers hold memory addresses. That's it. No difference between a variable of type int that holds a number and a variable of a pointer type that holds a memory address. The value types are just different, but a memory address isn't really any scarier than a number is. Just looks intimidating, which is kind of our problem, right? So that's what a pointer is. And we call it a pointer because it's sort of like this. My variable AR here, its value is, in my example here, 100. And that 100 is said to point to a place in memory where this array lives. So I'm gonna.
Now would it be AR99?
No. So this guy, we're going to say this is bucket 0, this is bucket 1, this is bucket 2, 3, 4, 5, 6, 7, 8, 9, like that. Now I'm going to put another set up here. These are all different ways of talking about the same things. I'm going to make this one, make these green. So this is 100. Now remember, we're storing chars, so we'll walk by bytes. So a char is 4 bytes. So this is 104 because the first char is in 100, 101, 102, and 103. Those are our 4 bytes being taken up by that first char. The second char will be 104, 105, 106, 107. 108, 112, 116, 120, 124, 128, 132, 136. Okay, and this is just in my arbitrary example where I assumed when we asked the operating system for memory to hold 10 integers, it gave me back the number 100. It gave me the base address of this new array, and it said, I found your land at 100. So my variable AR here holds the value 100. It does not hold this giant array. It just holds a piece of paper that tells me where I can find that array. So in my real life example where I said, if you have you go to a property that has 4 acres, somebody's going to give you a piece of paper that says, here's the address of the property. If you were to go to that property, you now have 4 acres of land you can work with. Does that make sense? Same thing's true here. This is the address where my array lives in memory. Here's the actual array that is in memory, starting at memory address 100. Okay, so this is just somewhere down the street. I said all of our memories on one giant street. So before I can get to the houses I just bought, I got to zip down 100 addresses down the street until I get to the beginning of the memory that was just allotted to me. And that's where I could start building my stuff. Okay. Now, at this point, I haven't actually put any numbers in here. I have, a plot of land that's 40 bytes big that I haven't done any construction on. I haven't put any numbers there. Okay. Now I can say I'm going to put a 4 here, and I'll put a 13 here, and I'll put a 1 and a 0 and an 8 27, 44, 3, 2, 5, something like that. So let's just assume I went ahead and I now put some stuff on my land somehow. We'll talk about how we actually can use arrays later, but just for our example here, we'll just say my arrays, just like strings, are 0 indexed. 4 is at bucket 0, 13 is at bucket 1, 1 is at bucket 2, so on and so forth. Okay, that's the way human beings like to think about our collections of numbers. So arrays, we have a single variable AR that points to my collection of 10 numbers, and I think about it as this is the number at 0, this is the number at bucket 1, at bucket 2, at bucket 3, at bucket 4. That's how I conceive upon my collections of numbers. You tell me where it starts and I'll walk through it to get my values. Okay, just like we did with strings. I'm telling you though, the reality is that the computer doesn't care about these numbers. The computer says, oh, this 4 is at memory address 100. This 8 is at memory address 116. This 3 is at 128. Okay, computers are operating off those memory addresses. We've already covered that we as humans think those memory addresses are a little bit scary, and we don't want to walk through things by the memory address. We want to have a more convenient mechanism that maybe maps to those memory addresses for us. At the end of the day, we're still using memory addresses. The computer is going to be using those memory addresses all day long, but if we can make it a little bit friendlier for us to work with, we will. We've already been working with strings, and reality is that strings are implemented as char arrays under the hood. So it's collections of chars. Those guys are stored in contiguous memory, and we've been using the functions from the string type to walk through that char in different ways, or to walk through the string in different ways. But under the hood, it's just operating off of this same kind of platform. So let's assume, I'll just show you a couple of examples of things here. Let's say I wanted to put this 8 here. So I'm kind of saying, how did I get that 8 into the array? I would have said AR at position 4 is equal to the 8. Okay, that's bucket 4. So I go to AR, I go to bucket 4, which says take 4 int size steps from the base address. How big is an int? 4 bytes. So I'm at the base address 100. I take 1 4-byte step. I take 2 4-byte steps, 3, 4 4-byte steps. And that's where I put that number 8. So this is the number of steps we're taking off of that base address. And how big is each step? It's the kind of value we're storing in that array. Now let me write the same thing in a scarier way. AR plus 4 times size of int. Well, what's AR? AR is 100. That's the value stored inside of AR, right? I add to that 4 times the size of int we said is 4 bytes. So that is 116. That's the math problem that got me to this value. That make sense? All right. So arrays need to be stored in contiguous memory. That goes back to what we said, how arrays are stored. They have to be stored in memory right next to each other so that this type of thing works. If you gave me the base address and you told me to go to a certain place in the array, I can mathematically compute where you've asked me to go because all the memory is next to each other. Go ahead. Yeah, that's kind of like what I did here. AR at bucket 4 is equal to 8. That's how this guy would have gotten there. Yep. So presumably I said AR at bucket 0 is 4. AR at bucket 1 is 13. AR at bucket 2 is 1. I just put them in. Yeah. Yeah. The only thing that's important here in terms of what was auto-generated is this stuff and this stuff. Right, but why did it increase by 4? Size of an int. If I was talking chars here, if I was having an array of chars, those guys are 1 byte big in C++. So I would take 1 byte steps instead of 4 byte steps. If I was working with Java, a char is actually a 16-bit, a 2 byte number because it uses Unicode. So that means I would take, so if I need to store 10 chars in C++, I only need 10 bytes. If I wanted 10 chars in Java, I would need 20 bytes. But 10 integers takes up 40 bytes because of how big they are. Good. Okay. So in any case, this syntax is going to be the most friendly for us, right? We all like that certainly better than crap down here, right? But the stuff down here is the proof that the other one works. All right. So questions about arrays so far. We haven't started using them yet, but what we should have learned from this lesson so far is how arrays are actually implemented under the hood from a memory perspective. Yeah, I mean, if I wanted to call this this variable LOL, I could. Yeah, this is just the name of my variable. I'm calling it AR because it's an array. All right, so yeah, because an object lives at an object. So really, an object is a pointer to a pointer. So if I was at bucket 0 of this, so if, in your example, you would have an array of player objects. Well, how big is a player object? A player object is a pointer to a place in memory where if a player has a first name and a last name, we're going to say, well, each of those is going to be a pointer to the beginning of a char array. Okay, so whatever all the variables inside of a player adds up to, that's how big a player is, but you're going to have an address that points to that dude. So this would be an array of addresses. Correct. But it would almost be as bad because now it's not a single contiguous array filled with gigantic values. Instead, it's a single array filled with memory addresses. Each of those memory addresses point to a place with a lot of data. That's one player out over here. Here's another player out over here, another player out over here. So the data still exists somewhere. We're just not forced to put it all right next to each other in memory. All right. So let's look at pointer syntax. Okay, so this is just kind of taking a step, not really back from arrays, but we're disconnecting from arrays for a second, and we're really talking about the syntax in C and C++ for working with pointers. All right, so we have two separate things. We have an asterisk, which says, give me the value at an address. And we have an ampersand. This says, give me the address where a value lives. Those are the two symbols that exist in C and C++ that allow us to work with memory. Now, something that's interesting is when you go to a more modern language, for instance, Java removes this syntax. Java says, we don't let you directly manipulate memory in Java. So we could say that maybe 95% of the time, that's a good thing. It protects the programmer. But 5% of the time, it takes away some of your superpowers to be able to manipulate memory. Realistically, from a beginning programmer perspective, we would say, well, Java's certainly friendlier. So then you would say, well, why are we learning C++ first? For the exact reason that Java is friendlier. For the exact reason that Python's friendlier. These newer, more advanced languages, let's say, have conveniences built into them that do make our lives easier as a programmer. But that doesn't mean that we don't need to actually understand what is happening under the hood, because that 5% of the time when we need to do something interesting, we're going to have to rely on that skill set. So sometimes, like I said, you might be in Java and you might be in a situation like, you know what, I really wish I can do something with memory here, and it's just the language won't let me. You know, you're kind of playing inside a, they got fences around you. All right. But the pointer syntax is going to feel intimidating when you start using it, for the only reason is that memory addresses are scary. For no other reason than they're just hexadecimal numbers and we're not used to them. All right, so let's look at a couple of examples here. Let's see, where am I? Do I have a... Here, I just have a 200 scratch pad. I can write some stuff in here. I'll just write it down here in main. All right, so I'm going to say int a is equal to 5. Now, if I do cout a end l, output of my program is going to be a 5 here. Here's my 5. Nothing new there, right? What if I say, give me the address of a? Way scarier, right? But what is that? That is the location in memory where that 5 is actually being stored in association with a variable named a. When I said I need to remember something, this guy right here, this creates a variable. I'm saying I want to remember something. Remember how human beings solve problems? We use our memory, we ask questions, repetition. Okay, and the way modern programming languages handle memory is through variables. So I'm creating a variable here. I'm saying I need to store the value 5 somewhere, and I want to associate that with the variable a. So that means the operating system is going to have to go out and find some place on that big long street to put that 5. This is where it found. It should have probably been different between runs of that. See? Each time through I run that, the operating system is saying, okay, let me go out and find a bucket that's free for you. Presumably this was running on the same machine somewhere else, and my last program still hadn't given up that location in memory. So, if I ran this and, millions and millions and millions of times, it would, I might be able to run the thing out of memory. Most modern operating systems have kind of like a protected area of memory for the user who's currently using the computer, and then so they can only take up so much. Otherwise, we had these examples of like denial of service attacks, where if you could get a program running on a computer with an older operating system, you could just go and have an infinite loop that just started requesting memory for arrays, or just creating variable after variable after variable after variable until the machine just ran out of memory, with no intent of ever using that those things, but with the intent of making sure nobody else could ever create a variable. Well, it's the same thing. Distributed denial of service attacks, the DDoS, is when you have it coming from a whole bunch of different locations, but really denial of service is when you attack an individual server and you're connecting to the server and spawning a computer program, creating a process. And most modern operating systems can only have so many programs running at once. The historic version of this is like an older version of Linux or of Windows NT, can have like 65,536 unique process IDs, which means if you somehow got 65,536 programs launched, regardless of what they did, as long as they were actively running, nobody could launch another program on that computer. There was no more unique IDs to hand those programs. Well, then you would say, oh, well, how do they fix it? Well, you just go in and start killing off programs. Except If you're completely out of process IDs, you can't even launch the terminal to kill the programs. You got to reboot. Yeah, so they've done some things to make that a little bit less likely at this point. All right. So we're seeing here's A and here's the address of A.
So what if you get the star, or is that not?
I'm getting there. All right. So A, all variables resolved to their most local definition. So A resolves to its value. The value of A is 5. That's what lives there. Okay. When I say resolve A to its value, which is 5, and I say, now give me the address where that guy was, it's going to show me that address where it found that value stored. Okay. Now I can create another variable. I can say an int pointer B. And I want this guy to hold the address of A. So the syntax for a pointer, when it's used on the left-hand side here, I'm creating with any kind of variable. We have the type followed by the variable name, followed by the value. Here's my variable name. Here's the value, but my type here is the type for an integer pointer. Not an int, but a pointer to an int. So this guy is a memory address. And the reason I've labeled it as an integer pointer is so that when I resolve it, it knows I'm going to a place that has 4 bytes. If I made it a char pointer, it would go to a place that had 2 bytes or 1 byte C++. So on and so forth. But this is saying I'm holding the memory address of an integer. That's what B is built to hold. And what am I going to put there? I'm going to put the address of A. A is an int. So now if I were to go in here and print out B, the value of B, this variable, is the address of A. So when I print out B, it's going to show me a memory address. Notice it's the same memory address as the guy above, because the address of A is where the value stored in A lives. B holds that same value, the address of A. If I were to print out star B, this says, go to this address, give me the value you found there. This will give me the 5. All right, make some sense? All right, so this is the syntax for working with memory addresses. And if I want to create a variable for holding a memory address, I put my variable type in, and then I put an asterisk after it, and that labels the type for this variable as I'm holding an address to one of these guys. Okay. But try your very, very, very hardest to not become afraid of addresses, because there's nothing scary about them once you realize it's just the number. And once you think back and say, oh, all of our houses are on one big long street, addresses in computers are actually far, far, far simpler than addresses in real life. But as soon as we see a giant hexadecimal number like this, we flip out. We could convert that guy to hexadecimal or to decimal, right? And it would just be an even bigger decimal number. But we'd be able to handle a little bit. This is going to be, I don't know, a huge decimal number. But what does that say? It's saying, well, I'm going to be heading down the street for a while, because it's not house 0 or house 1 or house 2. It's like house 2.5 billion or so, or something like that down there. Just a giant number. Hexadecimal allows me to store that number in a little bit smaller footprint. Back here, let's go to the converter. So this is what? That's 100,000, that's million, that's billion. So this is 140,723,164,974,412. That's the house number I'm going to. House 140 plus trillion, right? It's just a number. It's just put your hiking boots on is what you're going to do. Okay. Good thing is that because of the way our computer memory works is we don't actually have to start at bucket 0, then go to bucket 1, then go to bucket 2. We can zip down memory. They're kind of linked together and get there relatively quickly. Okay. All right. But that's what that value ultimately means. This value here is just a big decimal number represented as a hexadecimal value here. And that's a memory address. Okay, so now I'm going to go ahead and say int AR 10. And then we'll print out AR. So this defined for me an array capable of holding 10 of these dudes. And like we talked about here on the slide, AR gets the base address of that array, where the beginning of that land starts. There is what AR is equal to. The base address of that. All right, makes sense? Now I can go ahead and I can say AR at bucket 3 is equal to a 15. And then I can say cout AR at bucket 3. So I'm saying go to the base address and then take 3 integer size steps and tell me what you found there. Okay, so we're looking at syntax for arrays here. And there's my 15. I put a 15 there here, and then I say, oh, let's print it out. So in this line here, we're saying go to the base address of AR, take 3 integer size steps. So now you're standing in a place in memory, and then drop your 15 in that memory location.
Now, what if you had just a bunch of numbers, like 3, 15, 32?
Well, you can only, AR bucket 3 knows how to hold a single int.
Okay, but what if you had like 3, 15, 32?
You got to put it in more values.
Okay.
Yeah, so I mean,
It's just not-
I could do something like this. I can go through and I can say for int I is equal to 0, I is less than, we'll just say 10 in this case. I'm going to show you something else in a few minutes. I plus plus. And then we can say AR at bucket I is equal to, let's just say something like I times 2.
Okay.
So it would be 0, then 2, then 4, then, okay. So now when I print out bucket 3, it shows me the 6 there. If I print out bucket 7, shows me the value it found at bucket 7.
Yeah.
It's the 14, but this loop went through and actually put those values in there. Go ahead.
If you used to say print AR, is there a reason? See, that's one. Could I do AR bracket 0 or bracket 1 bracket 2?
What do you want to print out? AR what?
Not. I'm saying if I'm reading. Like, okay.
Yep.
Could I do AR 1 and just print out?
Yeah, you could.
Okay.
You probably wouldn't want to do that. It's a waste, but you could.
Syntactically, is there any difference with that and just?
Int A equals 5.
No, it's A is 5 and then there's. Which one of these?
Well, what does this guy produce? This guy produces a variable that holds a memory address to a empty location in memory that has no value there yet. So it's closer to B, except B holds a memory location. So really it would be something, it's not even that. I would say it's not like any of them, because this says we're going to create an array that lives actually somewhere in memory. And AR is going to have its base address, but this array only has one thing in it. So the array is only 4 bytes long, but there's nothing actually there yet. I haven't put a value there yet. So AR points to a place that has no value yet, but it is a place and it's something you own. Yeah, it's like you bought a lot of land. You know, you go and, you know, buy real estate, but you haven't built the house yet. Just empty. All right. Stack smashing detected. It's pretty funny. Yeah, I want to make sure that this right, yeah. I don't know. This must be a built-in thing, but it's okay. It's still showing me the So I'm going to go ahead and print out AR at bucket 0, and then I'm going to print out star AR. Now, when I put star in front of a variable, what does that say? Give me the value that lives at that memory address, right? You're going to see that both those guys were the same value. Now, maybe that was coincidence, right? So I'm going to say AR at bucket 3, and I'm going to say, give me the value at AR plus 3. Both of them are the 6. If we assume the base address from our example is 100, even though we know it's something scarier, right? This is the base address. Okay, so that's the base address of AR. If I add 3 to that, I'm walking 3 integer size bytes. So really what I'm doing is I'm adding 3 times the size of an int. So I'm adding 12 to that value. Because AR was built to hold integers. Because of how I defined it. Yep. Yeah. So this is called pointer math that we're doing here. So when I say add 3, it knows that since AR is an integer, that I mean 3 integer size steps through memory. And since we know integers are 4 bytes, this actually will add the number 12. 4 times 3 is the number of bytes it will add to the base address of AR. So this number right here plus 12 is where that guy lives. And we can see that. Let's see, I'm going to do the address of AR at bucket 3. I think that will show me what I want. So that's the number of bytes forward. Hexadecimal steps. Good. Question over there. Yeah. So I originally had it just like that. Yep. Let's go back to that here real quick. So this says go to AR and take 0 steps forward, which is at the very first value of AR. That's bucket 0. If we go back to this picture here, if I go to AR at bucket 100 right here, and I take 0 steps forward, I'm right here at the first value. In our example here, that's the value 1, 2, 4, 6, 8, 10, 12. Just make sure it matches up to what we have. So AR at bucket 0 gets me this value. But if I say, because that lives at memory address 100, but if I say star AR, that says, give me the value at memory address 100. And what's the value that lives at memory address 100? It's a 0. Because this is what AR is. So AR is a value. AR is a memory address. So if I say, here's this memory address, and I put a star in front of it, I say, tell me the value you found at that memory address. Well, when I built AR up here, so let me go back and let's switch this back to 10. I built AR right here. And what did this guy do? This found an address. Well, I'll say found a place in memory big enough to hold 40 bytes in this case, because I have 10 integers. And return the base address. So after this line of code, AR holds the address that is at the beginning of my 40 bytes. That's the value in that variable AR. AR does not hold 10 values. AR holds one value, and the type of value it holds is an address. So that address is the very beginning of the array. Go ahead. No, because all this loop is saying is I'm going to go through, I know there's 10 things in this array. So I'm going to put 10 things in there. So this array says, look, I'm going to go through and do something 10 times. That's all that for loop says, right? And what am I doing in here? I'm going to set AR, which is still the same base address that it used to be. But I'm going to go to bucket 0 the first time, and I'm going to put this number there. Then I'm going to go to bucket 1 the next time through, and I put this number there. Then bucket 2 and put this number there. I'm not changing the base address. I'm just saying, here's my array, put a value here, then put a value here, then put a value here, so on and so forth.
Now, what if it was too big for
Then you get an error because you're putting it into memory that you don't own. All right. So do you understand what this for loop does? Okay. So this guy does not change the structure of AR. It's just filling it with values. Correct. And we saw that when we printed it out right here. So this is the value of AR, the base address of it. But I just happen to know that if I were to start right here and start jogging down the street, I would have 10 more. Well, I'd have what, 36 more bytes of runway before I ran out of memory that I owned. Because AR just holds the base address of this array. We've given you 40 bytes. Here's where they begin. And that's where this syntax right here says, okay, let me go 0 steps from the base address. Then let me go 1 step from the base address. Now let me go 2 steps from the base address. And each time through, we're putting values there. We're dropping values at places in memory that we own. But then the interesting thing down here is these 2 lines do the same thing with 2 different syntaxes. Here's our friendly humans prefer this syntax, where it's saying, hey, this is array syntax. Here's my array AR. Just give me what lives at bucket 0. To use this syntax, you don't necessarily have to know how arrays were built under the hood, right? If you want bucket 0, just say AR at bucket 0. If you want bucket 6, AR at bucket 6. I don't care where that lives in memory. You just give me whatever's at bucket 6 in that guy, okay? So this syntax would be our programmer-friendly syntax. But that is actually saying the same thing as this, because this guy is star AR plus 0. Any value plus 0 is the value itself. So what value lives at the base address? The value that lives at the base address is whatever was at bucket 0. So this is AR in my example. That's why these two guys give me the identical value, because we are talking about the same place in memory in both cases. We're just talking about it in two different ways. The first way is using the friendlier array syntax. The second way is saying, hey, I love working with memory, so run to memory location stored in AR, and then give me the value you found there. Good. I think that's a fair way of saying. We'll call this guy friendly array syntax. As friendly as you're going to kind of get with that. And this guy is pointer syntax. I think that's a reasonable way of thinking about it. So what I'd say here is that a majority of the time for you, you'll use the array syntax. Because as programmers, we're creating tools and we're using those tools, and we don't need, things are already complicated enough, right? We don't need to make them any more complicated. But as computer scientists, we want to understand what's happening under the hood, because sometimes that can be beneficial. So this idea of being able to directly manipulate and walk through memory is a valuable thing. I can look at memory addresses. We can see that the address of, so I say print out the address of AR at bucket 0 and print out the address of AR at bucket 1. Those guys are 4 bytes from each other. There's our proof that contiguous memory. Or did we just get super, super, super lucky that it put the first 2 values right next to each other? So we can, say, okay, well, show me bucket 2 then. All right, maybe the moons have aligned. We're still getting pretty lucky, but it's starting to look like proof that it got us contiguous memory. All these buckets are right next to each other. Yeah.
So create a variable and assign corresponds to
Not random, but we're reliant on the operating system to hand it to us. So you could think of it as random if you want.
Is there a way to assign it to the step?
Well, you can. There's nothing. I mean, nothing says that you can't create a an int pointer. Let's call this guy magic address, and say that this guy is 0x. Well, let's see if I can just give it a random. See if it'll let me get away with it. More than likely, it's going to have like protected memory, so I might have to kind of fake it off of this, but let's just see if it will let me get away with it for a moment. Yes, I need to be able to say it's a hex value. Yeah, it's not gonna treat it right like that. Well, the short answer is yes. I just have to figure out how we can write the hex value. Something like this. But at the very least, this interpreter doesn't seem to be liking it. That's really what it should look like, is something like that. But basically, to answer your question, let's assume we could figure out how to get a hard-coded number in there. Presumably, that's an address that we don't own, right? But that doesn't mean that we can't do stuff with that address, because we didn't ask the operating system to get to it. This is kind of like us running over to our neighbor's house and we know where he lives. And this is actually how a lot of like bot programs work in software. They go to defined memory addresses where they know certain data lives, so they can extract that data. And that's why when there's like software updates, you know, like use World of Warcraft as an example, there was a lot of botting in that game. Every single time they released a new an update to the game, sometimes it was like an anti-botting update, they would change the location of their memory addresses. So now all the bot software would break for 2 days until the developers went and remapped where all the memory addresses were. So that type of thing. So the bottom line is, yes, you can create your own a variable that holds a memory address, but you might not own that memory address. And at that point, you would have to you could manipulate it depending on what level of protection the operating system had in to protect itself against you. All right, that makes some sense. Okay, so for no homework for Thursday, but I'll say a significant risk of a pointer quiz. Something where you're going to have to basically understand this kind of stuff up here and maybe the basics of arrays, but I probably not even arrays. Really understand this stuff. The idea between a literal value like an int, a variable that can hold an int, and a variable that can hold the address of an int, and how do you work with those two different sides of it? Go ahead. Look at this code and then kind of manipulate it and see what it comes down to. Here, I'll throw the link on Slack. I did just save it, so there's a starting point if you want to just kind of go in there and mess around with the code and make changes, things like that. All right, questions, comments, concerns, bribes. All right, I will see everybody on Thursday.